Good morning, good afternoon, and good evening. I'm your host, Caitlin Stulick. I'm here with our presenter, Angela Criswell, and our co-presenter, Ted Huang.
Hi, everyone.
Thank you all for attending Rigaku's webinar series, Mastering CT, Advanced Techniques in Practice. In this webinar series, we will discuss advanced X-ray CT methods to overcome common challenges, including high-density samples, repetitive routine work, and dynamic CT measurements. In this episode, we will be discussing automating workflows for X-ray CT. But before we start, a few housekeeping items. This is going to be an interactive session, and I will be posting relevant links in the chat window. We'll be taking your questions live during the webcast and answering them during the session, so please don't wait until the end to ask. Please submit those questions via the Q&A button at the bottom of your screen, as we won't be monitoring the raise hand function. We will try to answer as many questions as we can during the webinar, and will respond to any unanswered questions directly after the session is complete. If for whatever reason you have difficulty viewing the webinar live, please note that it is being recorded and you will be able to view the recording beginning tomorrow. Okay, and with that said, I will turn it over to Angela.
Thank you, Caitlin, and thank you to those who are joining us today for this presentation. So laboratories that have CT instruments often find that they measure the same types or similar types of samples over and over again. So take, for example, zoology lab that studies a specific species, or a student or postdoc in that lab might be tasked with scanning tens or even hundreds of samples of a species to characterize the morphological variation. Or maybe a lab performs failure analysis, and in which case you may scan the same part over and over and over again. So these are the types of cases that we'll be considering today when we talk about automating workflows for X-ray CT. And specifically today, what you'll learn is why repeatability matters when approaching these automated workflows. We'll talk about automating the CT scanning process, and we'll also talk about automating CT analysis. So first, why does repeatability really even matter? Well, if you were here for our last webinar given by Ted, he showed you an example of a 3D printed sample collected at different conditions. And you'll notice here that these two scans look very, very different. And if you were to analyze these with an automated analysis routine, then your approach to that would be very different. So collecting using the same scan parameters is important because it influences how you collect data. Likewise, these two scans of the same sample collected at two different exposure times result in very different histograms, which again, if you have an automated routine, then you might get very different results. So I would argue that repeatable CT is really going to give you better CT. If the scans look different, then automated routines can break. And in the long run, by performing repeatable experiments, this eventually can end up saving a lot of time and giving you higher throughput. And very importantly, it reduces error and perhaps the biases of individual users. And of course, the most important part is that it's going to improve data consistency across all of your samples and all of your batches. So very important to establish repeatability in your experiments. So with that, let's talk about CT data collection. But before that, we have a question for you. So I'm going to hand this over to Ted.
Okay, thank you, Angela, and hello, everyone. I would like to launch our first poll question of today's webinar. So here you see on the screen, we would like to know from your input that do you currently automate any part of your CT workflow? Like what Angela said, there is more than one. You can automate your CT scanning, you can automate your CT analysis, or are you already doing both to a certain degree? We would like to know that from you guys. So they will all be addressed today, but it's always good to know like what people already know and are still eager to learn about.
Yeah.
So I'll let it run for just a couple more seconds. We have a lot of response right now, and just another maybe 5, 10 seconds, and I will end the poll so everyone can see the result we have at the moment. So I'm going to end the poll right now, and I will share result to you. So it looks like a lot of people here haven't actually tried to automate, but that's good. That means you're here and you can learn a lot of things about it. And many of you have already started doing analysis part to automate the process. And some of you doing both, some of you doing scanning, which is good. It's a good distribution. I'm certain you'll learn a lot today. So with that, I would like to hand it over back to Angela to continue the webinar.
All right, thanks, Ted, and thanks everybody for answering that question. So half are not automating and about half are in different degrees. So I'm interested in everything you guys are doing. I'm always looking to learn. So if you want to share anything in the chat, so your tips, then feel free to do that as we move along through here. So first, let's address the question of automated CT scanning. And I would argue that the first step where you should think about is labeling your samples. So keep in mind that at the end of all of this process, you may have tens or hundreds of scans, and a sample label is important. And so is a picture of your sample. Always take a picture of your sample, even if you don't have metadata. Sometimes the general characteristics in your photo you can match up to the scan eventually. And of course, all metadata matters. So all vendors allow you to implement or take notes, and that is recorded in files that accompany your data throughout. So utilize that as best you can. Even better, however, would be to integrate a label into your sample so that the label persists with your scan. So for example, this gecko sample here, when it was collected, there was an embossed label included in the tube. And of course, we always have the sample ID there. If you're 3D printing samples, you might even add a label in that case so that it's always there. If you don't have that option, then you can manually scribe samples. You can't do that for everything. Some of these samples are very precious, or biological samples, you can't scribe them. But you might be able to with some, or you can use a silver pen to label, and that high density silver material ends up being visible in your scan. But no matter what, always capture information about your sample and include it into the metadata so that you can easily identify samples later and after you've backed them up. The other thing you want to think about when you're automating this workflow is how you're going to hold your sample, or how you're going to mount it in the CT instrument. And of course, the most important thing is that your sample holder and mount should basically get rid of any sample movement. And that's not just for a single part of your sample, but the entire sample. So if your sample is moving, then there may be portions of it that become blurred in your final CT scan. I would also suggest that you use a consistent and optimal orientation for your sample. So for example, we have some 18650 batteries. I wouldn't recommend loading them this way horizontally. Instead, the vertical mount is the ideal one, because the path length through the sample for the x-rays is the same in all 360 degrees. So consider your orientation when you prepare to mount your samples. And I would suggest designing and 3D printing some custom sample holders. So these are some that Ted and I use here in the lab. So for example, this one's holding a rock core. This is holding that 18650 battery. So you can inexpensively print some of these, or you can make some on your own. And some vendors offer systems that provide automatic sample changers. So this is an image from our benchtop system, and this is a turret, and this rotates around and the sample gets loaded into the instrument automatically, and there's a routine that you can run and run scan jobs. But don't worry if you don't have an automatic sample changer, all's not lost. You can kind of think of how you might devise your own. So I've seen some laboratories utilize things that stack samples. So for example, inside of straws or inside of tubes, there are some hobby stores that allow these stacking screwable containers, and I've seen those utilized as well. So essentially what you're doing is you're creating your own sample changer by taking advantage of the Z-axis translation within your instrument. And all of them have that capability. The height at which you can move will be determined by your specific instrument that you're using. So sample holders and mounting, think about how you can do this in an efficient way so that perhaps you don't have to be at the instrument for every single measurement. And then, of course, you have to establish your scan strategy and the conditions that you want to use. And this is a very important step. So we'll spend a little bit of time here. I won't go into all the fundamentals in much detail, but I'm going to mention a few important parameters, and we'll give you some references to resources so you can look at later to help guide you. So one of the important questions to ask yourself at this point is, what resolution do I actually need for my CT scans? And another question is, what X-ray energy should I use? And of course, how long should I scan my sample? The worst scenario would be that you end up with many, many, many scans, and then you find that they're not optimal to perform the data analysis that you want to do. That would be a horrible situation. So take into consideration these questions plus others that will be important. And the really important questions for you, of course, will be those that are influenced by exactly the type of scientific question you're trying to ask. So let's just look at that. So let's say, for example, I'm a geologist and I have a number of different rock cores. So they're different sizes, perhaps, different heights, different diameters. And my approach to each of these might be slightly different. The same is true, for example, if I look at batteries. The way in which I would collect data for this 4680 battery is very, very different than the one I would take if I were measuring something like this NMC cathode material. So I need much different resolution for each of these samples and would approach them differently. Same thing for biological samples. They come in a range of different sizes. Some may be stained, some may be not, some may be a harder material or a softer material, and each of these are handled a bit differently. So just to give you a scale here, this is a pad or that we lay on our sample loading, and each one of these squares is 10 millimeters or a centimeter. So just to give you an idea of the size range of these samples. So size definitely matters, and you really need to capture the dimensions of your sample, especially that maximum dimension. And ask yourself, okay, I want to see what's inside non-destructively. What are the estimated feature sizes that I expect inside our sample? So let's consider that for a couple of moments by looking at this sandstone. So it's one of those small rock cores I showed you previously. And if we collect data and look at a 2D cross-section of that data, we see here it was collected with this 9 millimeter field of view. And so obviously in this case, I'm probably interested in grains. I'm probably also very interested in this pore space because this is where any air, water, maybe oil or gas might be located. So how might I approach my CT scan parameters for this particular sample? So one thing I usually like to do is to collect the entire sample in a larger field of view. And if I do that for this sample, then the field of view in this case is 45 millimeters. Well, there's a general rule of thumb for all micro CT instruments in that the voxel size for a given field of view ranges from 1/3000th to 1/1000th for a field of view. And using that rule of thumb, it means that a data set collected at this field of view will generally give me a CT scan with 15 to 45 micron voxel sizes. And this difference usually depends on how you reconstruct or what reconstruction resolution you use. So considering this, if I look at a scan collected at that resolution and zoom in on a given couple of grains in this rock core, I can see they almost look like they're touching, perhaps overlapping. So if I'm interested in pore space, I'm going to miss some of this. So what I need to also then consider is, do I need to collect a second scan of my sample? For example, if I identify regions of interest, I may want to collect a higher resolution scan, or I may want to collect more than one of those. So just by moving the sample closer to the X-ray source, I increase the magnification of the sample and end up with a 10 millimeter field of view. And in this case, I have voxels that are somewhere in the range of 3 to 9 microns in that case. And if we take a zoom in here of that rock core and look at the pore space, then we can see that we're resolving individual grains and we get to the pores. So always think about, how many scans do I need to collect and at what resolution do I need to collect those scans at? So how about other characteristics? So you also need to consider, what exactly is my sample composed of? Because that will influence the X-ray energy and perhaps filter that you're going to use. So let's talk about that for a minute. But first, what I want to do is just to go back and recap, exactly what we are measuring. So we're measuring intensities that are transmitted through the sample, and the absorption of the X-rays will be influenced, of course, by how thick the object is, but also by its attenuation coefficient. And that attenuation coefficient is proportional to the density of our sample, the atomic number of the constituents in our sample, and of course, the X-ray energy that we're going to use. And you see that to the highest degree, Z and the energy are important. So keep that in mind as we go through the next few slides. And another thing I want to mention is, just for clarification, we're going to talk about KV and we're going to talk about KEV. So the difference between those, if you need a quick recap, is that KEV refers to the energy of the X-rays that we use. And KV, in this case, refers to the source applied voltage that we use. So for a 40 kV setting, we get a distribution of energies shown there in yellow, and likewise for other kV settings. And in general, a CT instrument is characterized by its maximum X-ray power that it can achieve. And the power is equal to whatever voltage you're using, in this case 40 to 130 kV, times the current. And that's usually expressed in either micro or milliamperes, depending on the instrument that you go to. So keep in mind the difference between these two as we go through the next few slides. So first, what is your sample composition? That's going to help you determine the right KV for your settings. And turns out you can calculate the attenuation, or you can look in tables to get the attenuation of your material and plot that versus KEV. One of the tools that I like to use is NIST's XCOM website. So Caitlin's going to put a link to that here. And so basically you can put in your element, a compound, or a mixture, and then get some specific KEV values. And another tool that I'll recommend that I use here in this presentation is one from Ketchum's lab at University of Texas. In his case, they created this MuCalc tool, which is basically an Excel spreadsheet that contains many geological compounds that are commonly found, and then give you some plotting tools. So in a sense, I sort of hijacked, I get my elements or compound information from XCOM, and I am plotting it and showing you examples here in this. So how does this actually work? So on the XCOM site here, I said I want to enter in a compound. You give it the chemical formula. If you're using the MuCalc tool, you want to output total attenuation with coherent scattering. And on the right side, you give the range in kV that you want to plot. Just keep in mind that this tool always uses units of mega electron volts. So I am setting it here from 0.01, which is 10 keV, to 0.1, which is 100 keV. And you can also enter in your own settings, for example, if you want to prepare your own plots in that case. So let's look at an example here of a sample that's composed of air, plastic, and water. So I basically just put some water in a Falcon tube and collected some data for it. But I'm interested in, okay, what is the absorption characteristics of these materials? And if I pull that information from XCOM and then I plot it using the UT's MuCalc tool, this is what I see. And so what I'm looking at here are absorption differences so that I get the best contrast here. And I see that it looks like 50 keV may be ideal, and that there's less contrast as I get to higher and higher energy. So for sure, this might be one setting that I use. I might start around 50 keV and maybe a few around there. And another thing, what I want to do is consider the filters that I will use. And it's really nice. MuCalc also has some plotting tools for that. So for example, you can give it an energy range, and you can select your filter and then find out what basically energy range is mostly filtered out. And it turns out we use aluminum filters quite a bit, especially for medium to lightweight materials. And then as we get to heavier materials or samples, then we shift to higher energy, and we might use something like a 10 filter, for example, for some of those heavier batteries. So take advantage of that tool as well there. So the other thing we want to consider is how long should I scan my samples? And I recommend you also at this point start asking questions. How am I going to assess image quality for what I've collected? So I chose a resolution setting. I'm going to choose a few energies to first test a few of my samples. I'm going to perform some scans at different times, but exactly how am I going to gauge whether this is a good scan or not? So I just wanted to give you some ideas that you might use. So for example, it might be most important, can I segment this so I can get to quantitative stuff? So the ease of segmentation or surface determination, perhaps if you're working with BG Studio Max and tools, might be most important to you. But there are also some other metrics like the signal to noise ratio and the contrast to noise ratio that you might also consider calculating for your data. And let's look at the use of these in a couple of examples. So first, we talked about the ease of segmentation and surface determination. The easiest way to segment data are using Otsu binarization for these two-phase materials. And in that case, you can see a scan on the left collected for a shorter time than the one on the right, and the histograms of these are quite different. If we were going to perform Otsu binarization in this case, we'd see we might cut right there. But if we collect for longer, we see, in fact, there are 3 peaks. And this smaller peak here is actually corresponds to some of the mounting material that's here. And Otsu binarization gives us very different results for each of these 2 scans. And it turns out that there are some areas in the scan that are over-segmented. So for example, there are some air voxels that are assigned to rock incorrectly, and here in the longer scan they're not. And we can see several different example areas of that within this scan. So it's very important to consider not only segmentation, but perhaps some other metrics. And that's where I want to talk about the signal to noise ratio and the contrast to noise ratio. So Caitlin will put a couple of references in the chat that are shown here below, from which I am showing how these are calculated. So let's go back to our sample, in this case, our water, plastic, air sample, and do some of these calculations for different energies. And of course, you want to do these at different exposure times as well. So here are 2D cross-section areas of data collected for that same sample at 50 kV at 160 microamperes, 90 kV 88 microamperes, and 130 kV 61 microamperes. And you're probably saying, hey, you're changing lots of stuff. Well, the important thing is that all of the scans are collected for 8 watts, basically a consistent power setting. And we'll talk more about why that's important in a few minutes. And what we want to do is to select a region of interest, or basically a bunch of voxels in the water space, in the plastic space, and in the air space, so that we can then calculate some of the signal to noise and contrast to noise ratios. So for 50 kV, rather, the signal to noise ratio for the water is 19, for the plastic is 18.6, and for the air is 11.1. So water is absorbing to a higher degree than this and the plastic and the air, which makes sense based on the plot we looked at previously. If we look at the signal to noise ratio for the data collected at higher kV, but same wattage, then we see the signal to noise is higher in this case. And even still at 130 kV, it's even higher. So basically there are more photons that are transmitted through the sample if we use 130 kV versus 50 kV. But I would also suggest that that's not the full story. What happens when we look at the contrast to noise ratio? So here I express the contrast to noise ratio of the water to the plastic and the water to the air. And for 50 kV, it's 6.4, for 90 kV, 4.9, and 130 kV, 4. So it turns out that if we use 130 kV, we might get higher signal to noise, but we can't, the grayscale difference between the water and the plastic is smaller. So in fact, 50 kV is a better setting to use for this particular sample. So that's how you can utilize those tools I just showed you to do some of these calculations for yourself. And we'll talk about some tools to do that later. So the other thing to consider then is, how long should I scan my sample? Well, of course, you want high X-ray, as high X-ray intensity as you can get, and long, but eventually there's a trade-off balance between those. So one of the things that you can do is you can turn up the power on your instrument and instantly increase the X-ray intensity. So we're going to look at that. You can also increase the exposure time per projection, or you can simply just collect more projections at that higher exposure time. So there are some strategies that you can use. And if you're collecting longer and longer scans, I recommend that you consider motion correction. And vendors of these micro CT instruments, including Rigaku, include tools to do that. And they may be called different things depending on what instrument you have. They may be called reference scans, or it may even be called motion correction. So have a look at those as well. So let's just look at cranking up the X-ray intensity, cranking up the power. So remember I said that the total wattage, or the total power, is equal to the kV you use times the current you use. And as we talked about in a number of different webinars, the kV setting that you use will influence the X-ray energy distribution that you get. It turns out the amperage, so the current setting, if you increase that, then you linearly increase the X-ray intensity. So you're thinking, I'll just crank it up, right? But you have to be careful because there's something else going on in these instruments. So it turns out that if you change the current, this is going to affect the X-ray focal spot size. And you ask, well, how does that work? So here's our X-ray source with our focal spot size shown here. And I'm going to zoom in and show you a bigger picture. And let's say that we want to turn up the X-ray power. It turns out that the X-ray focal spot sizes, focal spot size increases both vertically and horizontally in that case. And this happens because as you increase the power of the instrument, you also increase the amount of heat generated. And there is some defocusing that occurs with the instrument. So each of these depend on the specific X-ray source that you're using, but generally there are certain regimes at which you want to stay in depending on the resolution at which you're measuring or perhaps the field of view. So consult your documentation to learn more about that. Let's look at collecting data at different power settings and the consequence of that. We're going to go back to our rock core sample we saw at the very beginning. And in this case, this is a data set collected at 8 watts, a data set collected at 16 watts, and a data set collected at 14 watts. And what you see here is this blurring that starts to occur and the less sharp edges with the higher power settings that's caused by the defocusing of the X-rays. So always consider the amperage you're going to use and the power when doing these experiments. You can't just turn up the X-ray power and expect to get the same result. So we also talked about exposure time and projections. Well, it turns out there is a rule of thumb here, and the optimal number of projections is really a compromise between image quality, the scan time, and cost, because using the instrument does cost money, and you should carefully consider it. So what is that rule of thumb? Well, the rule of thumb is that you look at the number of pixels along the horizontal direction of the detector, and you multiply that times 1.5. I've also seen 1.6 as well, mentioned by Duplessis in that earlier reference that Caitlin shared with you. So, for example, if we have a detector with 2,000 pixels in the horizontal direction, then the estimated number of ideal projections is in the range of 3,000. But again, this is also something you want to test. So there are several journal articles that address the number of projections based on different scan goals, and it turns out they can be lower or maybe even more. So you want to investigate that with a few scans of your own. All right, so we've talked about quite a few things to consider, and now we want to automate our scan workflow. So first, we want to label it well, get that information about the sample into the metadata, determine our scan parameters that we are generally going to use, and do some TT scans of a small subset of your larger sample size. And once you identify the ideal scan parameters, then you can create what are called scan recipes and use that for all scans. And generally, the micro CT instruments will have a mechanism to do this. In ours, they're called jobs. And in that case, we can reuse the same job over and over again to make sure that we always are using the same parameters. And we may want to collect more than one scan. So consider that in your when setting up your workflow. Also important is when you get to the reconstruction step for your CT scans, which we did not talk about, you also want to use the same settings. And then as you have finished collecting all of your data, consider how you're going to back up all of this information and keep it in perpetuity, or at least for as long as you need that data to perform your analysis, perhaps your publications. And make sure you can always go back to know what your scan info is. So that's how we address automation of the CT scanning process. And now I just want to stop for a moment to see if there are any questions that you might have that we can talk about before we move on.
Okay, it looks like we have a question from an Adam. What filter do you recommend for unstained and stained biological samples?
That's a good question. So biological samples that are not stained, keep in mind the Z elements in there are carbon, nitrogen, oxygen. So very low Z, so you're going to use lower energy. And when you incorporate a stain, that's usually you want to increase contrast, so it's a higher Z element. A lot of times that could be tungsten, that could be iodine is a very common. So you want to shift to higher energy and probably start using an aluminum filter. So those would be some suggestions that I would have.
Okay. Sounds good. That's all we have for now. I would like to remind everybody, if you have questions, to drop them in the Q&A and not in the chat box. Okay, we have one more question before we move on, now that we've addressed that. A question from Bilal. How about the case of dual energy? How do we calculate the energy?
Yeah, so in that case, you're really looking at improving contrast in that case. So go back to use those tools. It's important to know what your sample is composed of, and look at and then plot the energy ranges, and you're looking for gaps, larger gaps, so that you have different settings. You're also looking at absorption edges for things in your sample, because you're going to see large fluctuations in intensity or absorption by your sample at those settings. So that's a great question.
Okay. Thank you, everyone. We can go ahead and move on.
All right, so we're going to go on, but before we do that, I'm really interested to learn more about what you're using to analyze your data. So Ted is going to ask the next and last poll question for this webinar.
Okay, thank you, Angela, and thank you everyone for going through the talk so far. Let me launch the second question so you can see it. We would like to know what CT analysis software do you currently use, because the next section Angela is going to talk about will be very integral to this. I know there's a lot of options, and it's never going to include all the tools that's available out there, but these are some of the common ones. Visual Studio, Dragonfly, Geodict, Viso, Image, Tomvis, Resizer, that's a long list, I know. So we have another option if these doesn't include any of your tools that you're currently using. It's a multiple option too. You don't have to just select one tool. You can select all the ones you use. So we will let the audience to give us feedback for a couple more seconds, maybe another 10 seconds, so we can see the results. And I'll show the results to everyone after that. So let me end the poll in another 5 seconds, and right now I will show you the result. So it looks like the most people use Image, which makes sense. It's an open source tool, and I started using Image starting my PhD. So that's a tool that everyone is very familiar with. And I also see a lot of Dragonfly, Visual Studio, and actually, people are using all of these on the list, and none of the tools is no one's using. So which is good. We have a very diverse audience here. So with that, I will stop sharing and hand it over back to Angela.
All right, thanks. And I noticed, Ted, that there were about 10% who are using something else. I know there's so many packages out there. I'd be interested to know what you're using. So in this case, please use the chat to tell me what you're using. I'd like to check it out. And then just make sure you ask your questions in the Q&A. All right, so let's move on then. And let's talk about automating CT data analysis. So why do you want to do this? Of course, we go back to repeatability and also speed. So if you're automating this process, it can speed up the analysis dramatically and reduce operator to operator variation and sample to sample variation, especially if you're going to take all of this data together, this quantitative information, and make comparisons. You want to have it consistent and allow you to enable comparison among your entire batch of samples. And of course, it's going to free you to do other types of interpretation. And also, I would just argue that even if you automate a few steps of your process, that can help a lot. So, and processing, keep in mind, can be sometimes the most consuming part of your time spent with these scans. So try to automate at least some of these manual tasks. And to start thinking about that, you need to determine what the absolute essential steps of your analysis workflow will be. And of course, you're always going to read in your data, but consider, are there any data corrections that you need to perform? So for example, do you need to normalize the intensity of all of your scans that you're inputting? Are there some important image processing steps that you want to do? The next step, of course, will be segmentation. Determine exactly how you're going to do that. Ideally, in a two-phase, Otsu binarization is the easiest, and sometimes in multiple phases if you get good contrast between them. You might also use tools like machine learning or deep learning, and you can automate that as well. And most important, what quantitative questions are you going to ask? Are you interested in volume percentages in area, surface area, sphericity of your pores, for example? So what steps are essential and what do you need to calculate? And also, are you going to perform any simulations? Many programs have simulation tools that you may want to use, and consider using those as well. And whether you're going to perform simulations for every sample or just a subset of selected samples. So I'm going to take a workflow, say porosity analysis, and just kind of iron out, for example, a few steps. Of course, first step is always going to be, I'm going to import my scan. I want to perform some image processing. For example, maybe I want to do some normalization of the intensities, or perhaps a non-local means filtering. And after that's performed, I have our two-phase rock sample, for example. So I'm going to use Otsu, and I'm going to label the most intense voxels as rock. And I'm going to invert that and label everything else as pore space. Keep in mind, if you have mounting material in your image, you may treat these steps differently. And then I'm going to compute some measurements on the regions of interest. And I may go on to do additional steps, maybe thickness analysis of ROIs and things like that. So it's good to sit down and map out and really write down or create an electronic document for exactly the steps you're going to use, because when you go into the tools and start automating, it's easy to forget certain steps. So sit down and plan this step well. Some of the tools that Ted and I have used in the lab to automate things are volume graphics, so VG Studio Max, Dragonfly, and Geodict. All three of those are things I have experience with. I'm really only going to focus on two of those tools today: volume graphics, VG Studio Max, and Dragonfly 3D World for the examples I give here today. And by the way, I don't know if you know, but yesterday, September 16th, the new version of Dragonfly 3D World 2025.1 came out, and I installed it and did confirm that everything I'm telling you and prepared in the weeks before is still true with version 2025. So what are the typical automation mechanisms that are used by these programs? Well, they generally work to automate things by creating macros. And when you go into the software, you start recording the actions that you perform via the user interface. And when you're finished, you say stop recording, and you end up with a macro. So this is from Dragonfly. You can see the watermark here. And this is the list of steps that I prepared for the analysis of this small rock core. So you can see Otsu binarization of the rock, and then the software updates the 2D and 3D views with the result. Yeah, we created the ROIs and so on and so on. Now, there may be some steps that you say, hey, I didn't do that, but keep in mind, this is a computer program and it literally needs each step. And so the software is going to take care of those intervening steps that are required. Once you're stopped recording, then what you do is you save this macro and then you play it for your other data sets. Or in some cases, the program may allow you to load many data sets and batch process them all at once. So those are generally the mechanisms used by both Dragonfly and VG, and Geodict is similar. So in that case, let's look at how I did this for our rock core data set. So this is, I think I need to switch back to turn that off so I can click on here. So here is the rock core just loaded into Dragonfly. I start the recording. I gave it a name here. Pretty easy. It's called MROI and compute. And I'm just moving it out of the way. And then I'm going to manipulate the interface in the sample view so that I get it to look exactly like I want. And in this case, I may want to save some 2D and 3D images, and all of the steps that we're doing here to adjust the 3D rendering, as well as the contrast, like here, is being recorded as we record this particular macro. And so I went on to add the additional steps and eventually stop recording, and I ended up with a macro. And then I can run that macro on a brand new data set just like this. I select it from the list and I simply say play. So all of these different steps are performed. And what I end up with at the end are some computations that are done on the pore space and on the grains themselves. So, and it ran in just a fraction of the time. So once you get it set up, even just doing these steps can make your whole process faster. And I also wanted to show you an example with VG. And one of the really powerful tools within VG is the surface determination. So one of the first steps, of course, is going to be, how do we determine the surface of this particular part that's undergone shear forces? So we want to look at these cracks that are generated from that shear force. So again, recording, set up my parameters so that I get just the part itself, not the cracks and not the mounting material, and then record that. And you'll see here what I did is I'm saving a macro that says it's only surface determination. And I'll address that in just a second. But eventually I created a job using mini macros, and this is what it looks like. So surface determination followed by some other steps that are listed here. And eventually what I end up with is a report that describes the cracks, their locations, and some calculations based on those. And this might be a very typical type of analysis that you might want to do, for example, end up with a report summarizing all your results. So you might have noticed there were a couple of different differences slightly between those two workflows, because there are different recommendations for macros. So in Dragonfly, it seems that you have one macro contains many steps, but the program authors of VG Studio Max recommend that you have many macros and then you group those together in jobs, because you might perform surface determination on all samples, but only perform specific, more specific tasks for some of them. So they focus on macros in job creation, and Dragonfly is macro. And of course, there's always a mechanism to customize these. So if you already know programming with Python, then you're in great shape because these use an underlying Python programming language to do this. And additionally, specific for Dragonfly, they do have some visual programming using Scratch. So if you're familiar with that program that was developed by MIT, then you can build up your building blocks, or once you create a macro, then you can modify it inside this visual programming environment. And you can also use Python, of course. So with that, I'd like to wrap up for today's webinar and just recap what we just learned today about why repeatability matters, how we might go about automating CT scanning, and some of the considerations that we should make. And then finally, quickly introduced you to some automated CT analysis tools. And hopefully I've left time for a few questions before we wrap up for the day.
Yes, we have a few questions here. From Felipe, using local tomography at submicron resolution often results in artifacts. Is there an ideal size or sample? Should it be roughly the same size of the field of view? What is the rule here?
Yes, that's a good question. So the general rule of thumb is that you want the sample to be less than probably 3 times of your field of view, or ideally very closely matched to your field of view. Because what's happening is that if it's much larger, then x-rays are going through and absorbing more of your x-rays that never end up actually in your image at all. So you're just creating noise where you don't have to. So try to have a sample that approximately matches your field of view. And of course, if you can't do that, then you can't do that. It's like in the cases of samples that are very precious. But for some of these submicron imaging scans that we're doing, we sometimes have the liberty of cutting it. So cut your sample.
Great. And then we have another question from a Heather. When should I consider data processing options like normalizing intensity or image processing?
Okay, so it really depends upon the workflow that you're doing. So I will tell you, normalizing intensity for your scans can be very important when you're using AI tools, because even samples are slightly different. Even though they're very similar, you might have minor fluctuations. And because some of those automated machine learning tools are based on grayscale, then you might want to normalize the intensity each time you read in a scan before, or make that a step in your macro before you perform the segmentation. The other one I think you mentioned was image processing. So in some cases, you can minimize noise by performing perhaps non-local means image and other imaging processing routines. And that might help get you to the point that you can use simply Otsu binarization for your segmentation step. So it really will depend upon exactly what your end goal and how you're going to segment your data.
Thank you. Looks like we have time for one more. It's an anonymous question. And what do you recommend you do for a carbon fiber flat coupon where it has a thin and a wide section?
Yeah, those are fun. Ted can tell you all about those. We get quite a few samples like that. And in those cases, the challenge is that you really need high resolution to resolve the fibers. But if you have this wide sample and you move it closer and closer, then you can't rotate 360 degrees. And if you're doing submicron imaging, you may be stuck that you have to cut the sample. However, there are some things that you can do. So you might explore using what are called half scans. So in that case, when you scan the particular sample that you have, you don't rotate fully 360 degrees, but instead you rotate somewhere in the range of 200-ish of them. So then what you can do is, let's see, I'm just gonna use this small thing. I can take my small thin sample, I can move it as close as possible to the source, and I'm only rotating like this, a half scan. And sometimes you can get a better resolution on the edge of your sample that may get you in the range of what you need to perform your analysis. So that's something you can try.
Sounds good. Looks like that's all we have time for today. If you had any other questions, we will follow up with you offline and get those answered for you. Thank you, everybody.
Thanks, everyone, for coming.
Okay, and that concludes today's webinar. Thank you, everybody, for joining us today. Don't forget to register for our next webinar in the series. This one will be covering 4D structure study with X-ray computed tomography. That will be on Wednesday Wednesday, October 15th. So
Yes.
I dropped the link to register for the next one there, and we look forward to seeing you then.